The feed drops at 6:20, not dramatically, not with ceremony. A pneumatic conveyor system on the upper deck of the feed barge opens its discharge valve, and 400 kilograms of compressed pellets moves through a 15-centimeter pipe and falls through the surface of Johnstone Strait in a column of brown and gray. Below the surface, 30 meters below, in a net pen that is 90 meters in circumference and 25 meters deep, 80,000 Atlantic salmon respond. They don't surge, they don't thrash. They orient toward the feed zone and consume. The pen is monitored by an underwater camera mounted on the pen's central mooring line at 8 meters depth. The camera feed goes to a screen on the feed barge, where the feed technician watches the fish behavior in real time. What he is looking for is simple. Are the fish eating, or are they leaving pellets to sink to the net floor? Uneaten feed sinking to the net floor means two things. First, the fish are not hungry, and continuing to feed wastes pellets and degrades water quality. Second, the system is out of calibration, and adjustments need to be made. The fish are eating. He watches for 90 seconds, confirms the consumption rate visually, and reduces the feed delivery slightly. The fish are slowing. He will feed again in 4 hours. This decision, more or less, faster or slower, what time of day, what water temperature, is made hundreds of times per day across a farm that operates 365 days a year. Feed is the largest single cost in salmon aquaculture. Managing it correctly is the difference between a farm that produces efficiently and one that doesn't. British Columbia's marine salmon aquaculture industry operates along the coast of Vancouver Island and the central BC coast, a geography of sheltered inlets, deep fjords, and tidal passages that provides the water conditions Atlantic salmon require. Cold, well-oxygenated, high-salinity seawater with sufficient current to clear metabolic waste, but not so much current as to stress the fish or damage the net infrastructure. The farms are not visible from the main shipping lanes. They are in the inlets and passages, attached to mooring systems anchored to the seabed, operating largely out of sight of anyone who isn't specifically looking for them. In a full year, BC's marine salmon farms produce approximately 80,000 to 90,000 tons of Atlantic salmon. That is a significant protein output from a comparatively small physical footprint. At each farm site consists of multiple net pens, typically 8 to 12 pens per site, suspended from floating collar systems, moored to the seabed through anchor chains and synthetic rope lines, serviced by a feed barge and a crew vessel that commute from shore. The infrastructure that makes this possible is engineered for a specific, demanding environment, an offshore marine setting with tidal currents, storm loading, biological fouling, and the weight of millions of kilograms of fish pressing against net walls and floors. Water is the medium. The net pen is the machine that holds it. The net pen begins with the collar. The collar is a floating ring. On modern farms, typically a high-density polyethylene ring, 90 to 120 meters in circumference, that supports the net below and the walkway and equipment above. When UHDPE floats are more resistant to UV degradation, impact, and saltwater corrosion than the steel pontoon collars used on older farms. The collar is not rigid in the traditional sense. It is designed to flex in wave action, distributing load rather than concentrating it at fixed points. Flexibility in a marine structure is a design principle, not a compromise. A rigid structure in wave action accumulates fatigue at its connections. A flexible structure moves with the waves and survives. The net itself is attached to the collar at its upper circumference and hangs freely below, weighted at the base by a ballasting system, a ring of lead or steel chain, that holds the net open against the tidal current. Without ballasting, a current will collapse the net like a sock, crushing the fish inside. The net volume, when properly inflated, approximately 15,000 cubic meters. The fish density at normal stocking, 15 to 20 kilograms per cubic meter. That is between 225,000 and 300,000 kilograms of live fish in a single pen at harvest density. The net holding all of this is made of nylon or polyester mesh, 35 to 50 millimeters bar mesh, depending on the fish size stage. The mesh is machine knotted or woven, and its tensile strength is tested for the design loads of current, wave action, and fish load before it enters service. But strength alone is not the operational challenge. The operational challenge is what grows on it. Biofouling. Within weeks of deployment in BC coastal waters, net mesh begins to accumulate marine growth. Mussels, barnacles, hydroids, bryozoans, and algae colonize the net surface in a succession that follows predictable seasonal patterns but varies by location, depth, and water temperature. A net pen in full biofouling condition carries significantly more weight than a clean net. The marine growth also reduces water flow through the mesh, reducing the oxygen exchange and waste flushing that the fish depend on. At severe fouling levels, a net pen under storm loading carries loads it was not designed to handle, because the fouled mesh has become essentially a solid surface rather than an open mesh. Net cleaning is a core operational task. The standard approach uses a remotely operated net cleaning machine, a device that travels around the exterior of the net on guide rails, using high-pressure water jets to remove fouling from the mesh. One cleaning pass takes 4 to 6 hours for a standard pen. Farms in BC coastal waters typically clean their nets every 3 to 6 weeks during peak fouling season, late spring through early autumn. The cleaning machines are operated by technicians on the pen walkway, monitoring the machine's progress through cameras, managing the power and water supply lines that feed the machine from the service vessel alongside. Clean nets mean oxygenated water. Oxygenated water means healthy fish. Healthy fish means productive biomass. The fouling removal is not optional maintenance. It is the operational baseline. 7:45 a.m., Site 4 has a net integrity alarm. The underwater acoustic fish counter, a sonar-based device mounted in the pen that monitors fish school distribution and movement, has detected an anomalous pattern in Pen 6. As the fish are aggregating at one side of the pen, rather than distributing evenly through the water column. This behavioral pattern is consistent with a current intrusion, a section of net that has been compromised, allowing current to enter the pen in a concentrated flow, pushing the fish into one quadrant. The farm manager calls the dive crew. 2 divers, certified marine aquaculture divers with 8 and 14 years of experience respectively, suit up on the crew vessel. They will do an exterior inspection of Pen 6 to locate the breach. Diving in BC coastal waters at a salmon farm site involves conditions that combine several categories of difficulty. Visibility in these inlets ranges from 3 to 8 meters, depending on season and tidal state. The fish in the pen create acoustic and visual noise that makes it difficult to maintain spatial orientation. The nets, when under current load, move very slowly, but enough to trap a diver's equipment if they're careless. The senior diver has done this particular type of inspection more than 400 times. He descends on the upstream side of the pen first. Upstream because current usually enters a net breach from the outside in. The upstream face takes the flow, and any weak section there fails first. At 12 meters, he finds it, a 30-centimeter tear in the mesh, at a weld point where the cleaning machine guide rail meets the net collar. The cleaning machine's rail has abraded the mesh over repeated passes until the material failed. Even the tear is not large enough to lose fish. The mesh deformation around it is still containment grade, but in another week it would be. He surfaces and reports. The repair crew deploys. Net repair underwater is a specialized skill. The repair kit is straightforward. A needle and twine made of the same synthetic material as the net, a cutting tool, and a weighted reference to keep the diver oriented during the work. The technique, tying the torn mesh edges together with a series of overhand knots, matching the original mesh geometry, is simple in description and demanding in execution at 12 meters and 5-meter visibility with current running. The diver works for 37 minutes. The repair is a 40-centimeter patch of new knots over the torn section, with a safety ring of additional knots around the perimeter to prevent propagation. He surfaces. The second diver verifies the repair from the exterior. The behavioral anomaly in Pen 6 resolves within 2 hours as the current intrusion is eliminated and the fish redistribute through the pen. The farm manager logs the incident. Mechanical abrasion failure at rail net interface. Pen 6 repaired same day. He will raise the cleaning machine guide rail by 5 centimeters to move the contact point away from the mesh weld zone. This is how operational problems are solved on a salmon farm, not with major equipment changes, with 5 centimeters of adjustment and documentation. The mooring system is the farm's connection to the seabed. At a typical BC salmon farm site, the mooring consists of a grid of anchor points on the seabed, concrete sinkers, embedded rock anchors, or driven steel piles, each depending on the bottom conditions. Connected by chains and synthetic rope lines to the pen collars above. The mooring must hold the farm in position against tidal currents, which in some BC inlets reach 3 to 4 knots at peak flow, and against storm conditions that can produce significant wave and wind loading on the exposed collar and net structures. The design loads for BC salmon farm moorings are set by DFO's aquaculture regulations and by engineering standards that require the mooring to hold the farm in position under a defined extreme event, typically a 1 in 25-year storm combined with the maximum current. Mooring inspection is done by the same dive crew that handles net repairs. Twice per year, spring and autumn, the full mooring system is inspected. Anchor integrity, chain condition, rope condition, shackle pin security, and the condition of the fair leads and cleats that connect the mooring lines to the collars. Chain corrosion is the primary concern. Steel chain in seawater corrodes continuously. The corrosion rate depends on water chemistry, temperature, and the electrical potential between the steel and any adjacent metals. A phenomenon called galvanic corrosion that accelerates in the presence of dissimilar metals in contact. Cathodic protection, sacrificial zinc anodes mounted at intervals along the chain and on the steel structural elements, slows the corrosion, but it does not stop it. The inspectors measure the chain link diameter with calipers at multiple points along each chain run. When the link cross-section has reduced to 70% of its original dimension, the chain section is replaced, not at 50%, not at 69%, at 70%. When the threshold is set to ensure sufficient safety factor remains when the next inspection cycle is complete. Conservative, deliberate, and non-negotiable. Oxygen management is the invisible control parameter. Dissolved oxygen in the water column around and inside the pen determines whether the fish are stressed or comfortable. Atlantic salmon require a minimum of approximately 7 milligrams per liter of dissolved oxygen. Below that level, their metabolism is impaired, feed conversion worsens, and disease susceptibility increases. In BC coastal waters, dissolved oxygen is generally high. Cold water holds more oxygen than warm water, and the tidal exchange at well-sited farms keeps the water column fresh. But there are conditions: warm summer water, low tide, high fish density, high feed input, heavy biofouling, that can combine to depress the dissolved oxygen in the pen interior. When this happens, the farm's oxygen supplementation system activates. Pure oxygen, stored in compressed form on the feed barge, is injected into the pen through a diffuser system mounted at the pen base. The oxygen dissolves into the water column as it rises through the pen, increasing the dissolved oxygen concentration inside the net. This is not emergency response. It is routine management of a parameter that the fish cannot manage themselves. Oxygen sensors mounted at 2 depths inside each pen feed continuous data to the farm management system. When the reading drops below the target range, typically 8 to 9 milligrams per liter, the supplementation system activates automatically. The farm manager reviews the logs each morning. A pen that is consistently requiring supplementation is a pen that needs attention. Either the fouling is too heavy, the stocking density is too high, or the site's hydrodynamics have changed. The oxygen number is a diagnostic as much as a parameter. 11 a.m. The wellboat has arrived. A wellboat, a specialized vessel with seawater tanks in its hull, essentially a floating holding facility for live fish, is mooring alongside the farm for a sea lice treatment operation. Sea lice are marine parasites, naturally occurring crustaceans of the genus Lepiopterus and Caligus, that attach to salmon and feed on mucus, skin, and blood. At low levels, they are a manageable condition. At high levels, severe sea lice infestations cause lesions, secondary infections, and significant mortality. They are the primary health management challenge in marine salmon aquaculture worldwide. The treatment method being used today is hydrolycer, a freshwater bath system. Atlantic salmon can tolerate brief freshwater exposure. Sea lice cannot. The fish are crowded from the pen by a pursing system. drawing the lower net up toward the surface to concentrate the fish, then pumped through a pipe in the wellboat, through a freshwater bath chamber, and back into the pen. The freshwater contact time is approximately 30 seconds. For the fish, mild stress, rapidly resolved. For the sea lice, lethal osmotic shock. The wellboat's treatment chamber processes approximately 200 fish per minute. A full pen treatment, 80,000 fish, takes approximately 7 hours. The fish handling must be precise. Fish crowded too tightly sustain physical damage. Fish moved through the pipe at the wrong flow rate sustain scale loss. The pumping system's impeller speed, the crowding density, the freshwater temperature, all are managed by the wellboat crew with the farm's fish health manager present throughout. The fish health manager has a veterinary degree and 4 years of field experience in aquaculture. She watches the fish coming off the treatment system into the return pipe. She is looking at their behavior. Do they swim normally in the return flow, or do they show signs of handling stress? They are swimming normally, she confirms. Continue. The hatchery is the beginning of the system. The fish in pen 6 on site 4 were not wild caught. They were hatched in a freshwater hatchery, raised to smolt stage, the physiological transformation that prepares a salmon for saltwater life, and transported to the marine farm site by wellboat. The hatchery operates on a production cycle that is almost entirely decoupled from natural seasonal timing. Temperature-controlled water systems allow managers to accelerate or retard developmental stages. Photoperiod management, controlling the hours of light the fish receive, controls the timing of smoltification. The result is a consistent, year-round supply of seawater-ready smolts to the marine farm sites. Smolt quality is the foundation of marine farm performance. A smolt that has been through a stress event in the hatchery, a disease outbreak, a handling incident, a water quality failure, may look normal at transfer but will underperform in the marine environment. A poor osmoregulation, increased disease susceptibility, reduced feed conversion, all traceable in retrospect to smolt quality. This is why the hatchery records matter. Every fish cohort that enters a marine farm carries a data trail: hatch date, vaccination history, feeding records, health treatments, water quality logs for every week of freshwater rearing. The marine farm manager receives this information at smolt transfer and uses it to calibrate expectations and monitoring for that cohort's entire marine phase. The fish in the pen are not anonymous. They are a documented cohort with a known history. 1430. A Pacific storm system is forecast to make landfall on Vancouver Island in 36 hours. The Meteorological Service is predicting sustained winds of 55 knots with gusts to 70. Wave heights in exposed inlets, 3 to 4 meters. Sea tidal current at peak, 3.2 knots. The farm manager runs through the pre-storm protocol. All mooring lines inspected and tightened. Slack removed from the shackle pins. The feed barge positioned on the leeward side of the farm, where it will be partially sheltered by the collar array. The underwater camera system secured against movement. The oxygen supplementation system checked. Storm conditions can lower dissolved oxygen as wave action disrupts the pen interior. All the preparation work is done before the storm, not during it. During a 55-knot wind event, no one is working on the pen walkways, the nets, the collars, the moorings. They will manage the storm without human intervention. They are designed to, but the design has tolerances, and the tolerances assume the pre-storm preparation was done correctly. The farm manager has been through 14 of these storms in his career. He knows what happens when the preparation is incomplete. He does not leave anything incomplete. The storm arrives at 2:40 the following morning. The pen monitoring systems log elevated current speeds, net deformation within acceptable limits, dissolved oxygen holding steady, the supplementation system cycling on and off to compensate for the increased water mixing in the storm conditions. At 7:15, the wind drops to 30 knots. The farm manager makes his first walkway inspection at 8:30. Mooring lines holding, collars intact. Net ballasting in position. No fish loss. The system absorbed the storm. Harvest is the endpoint of a 16 to 20-month production cycle. The fish that were transferred to the marine site as 80-gram smolts have reached a harvest weight of 4.5 to 5.5 kilograms. The pen contains approximately 400,000 kilograms of fish. A wellboat moors alongside. The pursing system crowds the fish toward the surface. The pump draws fish from the pen into the wellboat's holding tanks, gently at a speed that minimizes scale loss and physical damage. Live fish arrive in the holding tanks and are held there for the transit to the processing facility. The transit takes 4 to 8 hours, depending on the facility location. At the processing facility, the fish are slaughtered by crowding into chilled seawater, a method that produces rapid loss of consciousness, followed by death in conditions that minimize stress hormone levels in the flesh. High stress at slaughter degrades meat quality. The flesh quality that a consumer experiences at a restaurant in Vancouver or Tokyo was influenced by every decision made on the farm for the preceding 18 months. The feed formulation, the dissolved oxygen management, the handling practices, the sea lice treatment timing, the slaughter method. Each decision is recorded. The traceability chain runs from the consumer's plate back to the hatchery. British Columbia's salmon aquaculture industry produces protein with a feed conversion ratio, the kilograms of feed required per kilogram of fish produced, of approximately 1.1 to 1.2. This is among the most efficient large-scale animal protein production ratios in any food production system. Annual production, 80,000 to 90,000 tons of Atlantic salmon. Export value, over 600 million Canadian dollars annually, primarily to the United States, Japan, Western European markets. Number of farm sites operating under DFO license on the BC coast, approximately 100. The people operating these sites, the farm managers, the dive crews, the feed technicians, the fish health managers, are working at the intersection of marine biology, structural engineering, logistics, and veterinary medicine in a coastal environment that operates on its own schedule regardless of production targets. The tidal current does not adjust for the harvest window. The storm does not check the mooring schedule before arriving. The sea lice arrive when conditions favor them. The farm has to be ready for all of it, every day, in waters that are cold, productive, and indifferent to what is being asked of them. Under this video, there's a subscribe button. It's a small action, but it helps keep stories like this afloat. If these systems fascinate you, the quiet force of water held in place by engineering and discipline, subscribing simply means you want to see more of what operates beneath the surface.